Welcome to Sundar's lecture. This is lecture number 74, and in this lecture we are going to see transient responses of RLC series circuit for DC input. See what we have done in the previous classes. Just we have gone for AC transient responses of AC circuits for AC input. We have seen RC circuits, and for DC also we have seen we have separately seen RLC, and then we have gone for RL and RC. And we have not seen RLC. I have to teach you RLC separately. That is why I have not taken a class about RLC series circuit before this one. So now in this class we are going to see transient responses of RLC circuit, right? Now what we are going to get by an expression here, we are going to get what is the V of t expression, and then it is very easy to get what is the I of t expression. What is I of t? Since this is the series circuit, what will be the value of I of t? So I of t will be obviously is equal to C into dV divided by dt. That we know, right? Whatever it may be, if this is plus and this is minus, where if current enters from plus to minus in a capacitor, then obviously the current through the capacitor value will be C into dV by dt, right? We know this one. Now what we are going to do, we are going to just write the KVL expression for this circuit. So we are going for KVL expression. What you will get, so the current direction is like this, so it will be from minus to plus, it is plus E, and the current is going in the same direction as we are going, so it will be minus I of t into R, and then it will be from plus to minus I am moving, so it will be minus L into di by dt. These kind of things and all we have already seen, right? What is the voltage across the inductor? It will be L into di by dt, and then it is minus V of t, that will be is equal to 0. Now this is the expression by KVL, right? Now what we are going to do, we are going to just simplify this equation, right? What I will get, it will be I into, maybe I will write it as I into R plus L into di divided by dt plus V of t, maybe V of t or V, which is equal to E. Now what you do, you just substitute this I of t expression inside this one. What you will get, you substitute this value here, it will be RC and dV divided by dt, you will get like this, and then plus this is L, and then there is a C, so it will be LC, d by dt of dV by dt. So what you will get, it will be d square V divided by dt square, and then plus it will be V of t, which is equal to A. See, what is this one? This is nothing but second order differential equation, second derivative, right? This is the second derivative, and first derivative are constant, which is equal to the right hand side excitation function. And what we do, we always go for a constant before, which means number one constant before the derivative, first derivative, or it may be here it is a second derivative. So what we do, we have to divide it by LC. Divided by LC, what you will get, so first I will write down this expression, maybe I will write it in a different color. So it will be d square V divided by dt, LC will be cancelled out, plus RC divided by LC. So CC will be cancelled out, again other terms will be RL dV divided by dt, I can write like this, and then plus V of t divided by RC, right? So V of t divided by RC, sorry, not RC, it will be LC, right? So it will be LC, which is equal to E divided by LC. This is the expression, and you see this is the second order derivative equation, and we know how to find the values of characteristic equation and how to solve the second order differential equation to get the value of V, right? There are three conditions are possible here. See, if it is a first order differential equation, then it is not a very big problem, because in first order differential equation you will straight away get the value of characteristic equation. Maybe we are calling it as D or S, it may be anything, but you will straight away get the value. But if it is a second order differential equation, then obviously you will get S1 and S2, or maybe D1 and D2, right? We will take it as S1 and S2 here. Maybe I will write down this expression as, see, I will write down this expression as S square. Operator I have taken it as S here. So S square plus R by L into S plus, and then here it will be V divided by LC. Not V divided by LC. I will write it as 1 divided by LC, and that should be is equal to 0. What is this one? What is this one? This is nothing but characteristic equation. Characteristic equation, right? We will write like this, a constant value, right? Characteristic equation. And you see what I am going to do. I am going to take two new terminologies, and those two new terminologies will help you to understand the circuit very clearly. And what is those two terminologies? See, I am going to take damping ratio. Damping ratio. What is this damping ratio? I am going to explain you a bit clearly what is damping ratio and what is going to happen in this RLC circuit while storing the voltage in the capacitor. All those kind of things we will see very detailedly. But before that, you try to understand damping ratio. I am just taking the damping ratio as alpha which is equal to R divided by 2L. This is the value of damping ratio, and I will tell you why I am taking these kind of things, right? So next, what I am going to do, this is nothing but natural frequency, and I'm just going to take that as omega naught, which is equal to 1 divided by root over LC. 1 divided by root over LC. And see, from here, from these two expressions, I can easily write what is the value of RL, R divided by L from this. What is the value of R divided by L? It will be 2 alpha, right? And I can write like this. And also, what is the value of 1 divided by LC? It will be omega naught square. Omega naught square can be written as what? 1 divided by LC. Right? You just square both terms, you will get this value. And now what you do? You just substitute this terms here inside the expression, in this expression. Maybe what is the expression you will get? You will get S square plus 2 alpha S, and then plus it will be omega naught square, which is equal to 0. Now you see, this is the value. This is the expression for characteristic equation. See, right hand side E by LC will be there while finding the solution for differential equation. Obviously, you are going to use this expression. You don't worry about that. I am just explaining you how to calculate the characteristic equation for this particular circuit. Not this right hand side excitation function will come while solving the differential equation, right? We will see that one clearly. Now, if this is the expression, then obviously you will get S1 and S2. What is the formula to find S1 and S2? We know, right? What is the formula to find the quadratic? This is actually quadratic equation. If you simplify the quadratic equation, what is the formula you have to use? Obviously, you have to use S1 comma 2 can be written as minus B plus or minus square root of B square minus 4 into A into C. It is whole divided by 2A. This is the formula, right? We know this one clearly. Already we have seen these kind of things, right? So now, what is A here? A, which is equal to the coefficient of S square term, it is 1. What is the B value? Coefficient of S term, that is nothing but it is 2 alpha. And then what is the value of C? Constant, which is nothing but here it is omega naught square. That's all. That's all. First, what you do. So obviously what you can write it down here, maybe S1 which is equal to minus B plus square root of B square minus 4AC whole divided by 2A. This is one term. And what is S2? S2 will be minus B minus square root of B square minus 4AC divided by 2A. This is the two terms. Right? This is the two terms. Maybe if you find one term, then obviously you can write the second term too. If minus B, then it will be plus. Anyhow, we are going to get what is S1 and what is S2. I will bring it to the next page. Right, now what you do, you just try to substitute in this expression. What is the values? See, S1, maybe S1 can be written as, see, S1 which is equal to minus B. So it will be minus 2 alpha, and then it is plus square root of, what is b square? It will be 2 alpha the whole square, and then it will be minus 4 into a is 1, so I don't need to put here, and c is omega square, so it will be omega square, omega naught square whole divided by 2 into a, it is 2, right, into 1 it will be, right. So S1 will be is equal to 2 alpha plus, see what I can do here, this one can be written as 4 alpha square minus 4 omega naught square, and then it will be whole divided by 2, and what I can write here, S1 can be written as 2 alpha, if you take 4 outside commonly, and then what you do, square root of 4, or you write it as, yes, it is 4 and alpha square minus omega naught square, this is the value, whole divided by 2u, this is the value. And now you see, this 4 can be written as what? 4, square root of 4, and then it will be square root of alpha square minus omega naught square. What is the square root of 4? It will be 2. So take 2 commonly outside, what you will get? If you take 2 commonly outside, S1 will be is equal to 2 alpha plus 2 square root of alpha square minus omega naught square whole divided by 2. If you take 2 commonly outside, every 2 will be cancelled out, and what is the S1 value finally? S1 can be written as alpha plus square root of alpha square minus omega naught square, right. This is the final value. This is the final value of S1. Right, if you similarly simplify the same expression, similarly, I will directly write, I am not going to solve similarly, what you will get, S2 will be same, the value of plus will, so here it is minus, right, so I missed out minus, see this is minus, this is minus, this is minus, and this value is also minus, right. So, so this value S2 will be now minus alpha minus square root of alpha square minus omega naught square. Now, this is the value of S2. This is the value of S2. See, you try to understand one thing clearly here. We will get two roots, two different characteristic roots for this expression. To find the characteristic equation, you will get two different roots. See, we will have three conditions here, right? I will write down the three conditions, and then you try to understand what those conditions and when it will be applied, right? I will tell you that. See, the first condition, we are calling it as overdamped. Why this is overdamped? See, try to understand one thing clearly. This E, the value of voltage E, that is the applied value, right? This is constant, right? This is DC input constant, and this E will be stored in the capacitor in three manners. In three manners. What is that three manners? What are the three types so that the value of E can be stored in the capacitor by three ways? Maybe you write it as three ways. One is overdamped, one is critically damped, and the other one will be underdamped. See, when this overdamping will happen, this overdamping will happen when alpha is greater than omega naught square. Sorry, not omega naught square, it will be omega naught. This is the condition. This is the condition. And then you go for the second one. And here, how roots S1 and S2? What happens to S1 and S2? If this condition applies, maybe I will write it as R by 2L greater than 1 over root LC. This is the condition. And if it is so, then S1 and S2 will be distinct. What is the meaning of distinct? It will be different values. S1 will not be equal to S2. That's all. That is the only thing. Right? So next case number 2. Case 2. What is this case? It is critically damped. Critically damped. And what this case explains is, see, while critically damped, the value of alpha will be equal to omega naught, which means R by 2L value will be is equal to 1 over root LC. This is the condition. And here the value of S1 will be equal to S2. If both S1 and S2 are equal, then we call it as critically damped condition. and then you go for case number 3, case 3, and this is nothing but underdamped. What is this underdamped condition? See, you take here in this condition, alpha will be less than omega naught, or omega naught will be higher. So this value r by 2l will be less than 1 over root LC. And what happens in this condition? S1 and S2, S1 and S2, this is very interesting. This value will be complex conjugate. This value. Both will not be same, distinct, it will have a different values. Here both S1 and S2 will be same, and here S1 and S2 will be complex conjugate. This is the 3 different ways where you can see the capacitor can store the value of E, applied E in it. See what will happen. I will directly draw a diagram to understand how this one will looks like. See, let maybe I will write it in a different color. Let E is equal to 10 volt. Let me write like this. Maybe if this is the voltage across the capacitor and this is the 10 volt, applied 10 volt, and this is the time axis. And see, one thing, this 10 volt will be reached immediately after some time, after certain time, like this. Or it will reach, will be a different color, or it will take so much time to reach the value of E. This is one condition. Maybe this will come like this, maybe, and this value will reach like this. And the other condition here, what will happen? This value of E will be like this, and it will reach up like that. See, you try to understand one thing. These are the 3 different conditions. See, if it takes longer time to reach the value of 10, this is the capacitor voltage, this is the input voltage E, and this will be overdamped. Condition. And you see this value, this one, if it reach immediately after some time, maybe not, it will take some reduced time to reach the value of 10 volt, then that condition will be critically damped. And this value you try to understand. If it oscillates, then this condition, I will write here, this condition, which is nothing but underdamped. What is this? This is underdamped. That's all. That is what we have written here. This is how the voltage in the capacitor is going to, see, the value of input voltage will be stored in the capacitor in these 3 manners. And we are going to take certain examples with the numerical values in the next class, and we try to solve that problem, and we try to analyze how the voltage in the capacitor looks like, or the value of input voltage is stored in the capacitor. See, if you understand these 3 conditions clearly, then it will be very easy to understand so many things. See, oscillation, why it is coming, see, very simply you can understand it in another way. What is the phenomena of LC in a circuit? It tries to oscillate. We have seen these kind of things. Already we have seen LC circuit will oscillate. And you see, if LC is more than R by 2L, then obviously it is going to oscillate. That's all. If resistance is high, then it will take longer time. Thank you. We will see in the next class.